Okay. It is now recording. So,
Okay, thank you.
well, you asked about number 21 on the homework. And we're wanting to know if it is convergent or divergent to justify the answer. I apparently forgot to pick up a blank copy of the packet, of the homework packet, when I went to school. But looking at it, you would then do L'Hopital's rule. Because if you try to plug it in at first, essentially you just want to take the limit as n approaches infinity of sine of 1 over n over 1 over n. And if you take that to infinity, 1 over n on the inside, as it goes to infinity, would go to 0. So that'd be sine of 0, which is 0. And plug infinity in on the bottom would also go to 0. So it goes to 0 over 0, and then you apply L'Hopital's rule. And after you do L'Hopital's rule, that is when you get cosine of the inside times negative 1 over n squared, because derivative of 1 over n is negative 1 over n squared. That's just because when you do L'Hopital's rule, it's derivative of the top over derivative of the bottom, and then that's also chain rule there. And then derivative of the bottom would be also negative 1 over n squared. Well, then those things would cancel, and you would only be left with limit as n approaches infinity of cosine of 1 over n.
Oh, okay. Well, still, because I was like, it's still over n squared, but it just cancels.
So those two different parentheses would end up canceling. You just have limit as n approaches infinity of 1 over n. And then that's when you plug in the infinity, that's cosine of 0, which is 1, so it converges.
Gotcha. All right.
Okay. How many people do we have in here now? 9. I'll wait a little longer. Okay. One announcement. Most of you should have seen in my message this morning that every weekday at 8 a.m. all the way through May 1st, we're going to have a live YouTube review session from some of the calculus teachers who I've even gotten their resources before. And because of those, and some of the lessons we do next week and maybe later, I'm not going to do absolutely every example. I'm going to add more just question and answer time because if you watch those, which you should, they're also teaching the same content as well. But the past 3 days in those lessons, they were doing parametric and vector equations. And I know they're not on the exam, but the rationale behind why they still did it is because they still ended up, through covering that, covering differentiation and integration and particle motion and function analysis throughout all of that. Particle motion then does it in 2 different dimensions. So they were still covering review material, and parametric equations is in the course. But then next week they're going to start covering what we started covering on Wednesday as well. So
after that, are they just going to cycle around to the other units?
So
and things like that?
They are doing 13 lessons of units 9 and 10, and so they already did, at least I think so. And then 15 lessons of all review material. So every weekday until Friday, May 1st, they are doing review sessions at that YouTube channel that I sent. And the last 3 weeks of that, 3 weeks right before the exam, it's all going to be review stuff of both AV and PC review, just reviewing any topics that are necessary for the AP exam. They'll talk specifically about this year's exam and probably go over tons of different time and free response questions. And through those two people doing those review classes and other people, I've acquired some great free response questions that are very similar to what people think this year's test will be like. And so I'll send those out to you once we start doing review for you to work on, and then we'll discuss them at some session. But those videos are very good to work on, to watch. Obviously, if it goes live at 8, I mean, you don't have to watch it right then. You can watch it some other time. You can watch them all in a few weeks. You don't have to watch them right now. Okay. How many people do we have in here now?
Mr. Hunter.
Yeah.
I don't know where to start studying because like there's a lot of resources now. Like there's the AP classroom and there's Khan Academy and there's still the packets that you give us.
So for AP classroom, I would hold off on that right now until we start doing review stuff.
Okay.
So right now through about from now till April 8th or 9th, from now through April 8th, we're just going to be working on this unit of sequences and series. With the expectation if we do come back to school on April 13th, hopefully we do, and if and when we do come back to school on April 13th, we would then have a test over sequences and series unit that week we get back, probably April 16th. But starting April 8th, I'll then we'll start doing all sorts of review stuff. And that will be the purpose of AP Classroom, that we will use AP Classroom and the progress checks under each unit as review. So right now, I will be posting the key to the notes and homework packet of this current unit. And right now is just sequences and series. Don't worry about reviewing past stuff yet. And then using Khan Academy or the other YouTube review channel I sent out this morning as ways to learn the current unit.
Okay.
And starting April 8th, I'll start giving you review stuff to work on.
Okay.
If we were to buy an AP book, which one would we buy?
The Barron's, I heard has been recommended. Barron's AP Study Guide. That's the one I have. Any other questions before we begin the lesson? So I have worked out a few kinks on Wednesday. I didn't know how to show the hover cam without doing the share screen. I figured out that earlier. So I'll be able to see any questions you put in the chat bar today. Okay, well, if you don't have any more questions, we will go ahead and start. What just happened? Oh, that. That is annoying. Yeah, never mind. Do it the way I did before, I guess. Okay. Share screen. Share. Okay. There we go. So here's the camera. We're on Infinite Series. An infinite series. Well, we talked about sequences on Wednesday, and a sequence, just a list of terms, and we're going to define a series, or S sub n. It's representing the sum of a sequence. A series is a sum of a sequence. So S sub n, summation from I equals 1 till n of a sub I, where a sub I, this a sub 1 all the way to a sub n represents the sequence. And just the subscript, again, represents whatever number you are on in the sequence. And so S sub n is the summation of all of those numbers in the sequence until you get to the nth term. So if it's just S sub n, then that's the sum of the entire sequence, as n goes to infinity possibly, or just sum from a sub 1 until a sub n. Of if n it could be some very specific number. An infinite series is one where we're going to call an infinite series just capital S, and that's taking n as n approaches infinity. So sometimes you will still see an n up here, but it will be the limit as n approaches infinity of that summation. The general term of a series is a expression that represents the nth term of the series, an expression that represents the nth term. So the summation from n equals 1 to infinity of 3n is this, and that 3n right there, which can also be written over here, that is the general term that represents the nth term of the sequence. An infinite sequence that converges has the nth term approaching some actual limit. There's no way an infinite series will only converge if it approaches some limit. And an infinite series will only converge if the sum of that infinite number of terms approaches some limit. And so, again, a series is a summation of a sequence. And so if we're adding a whole bunch of terms over and over and over again, adding them, eventually we need to add nothing so that the entire summation approaches something. If we just keep adding more and more real finite numbers, it's going to keep going up to infinity, maybe slowly, but it will keep going up. We say that a series converges if the sum of all of those numbers does actually approach some value. So S sub n, which represents the summation of n many terms in each sequence, would equal some capital L. And if it does go to infinity, if the sum of all those numbers goes to infinity, then we would say it diverges or is divergent. So looking at number 1, let's write out the first few terms first. So this means, well, if n is 1, then we have 2 to the first power, which is 2, plus if n is 2, we have 2 to the second power, which is 4. N is 3, we have 2 to the third power, which is 8. And then if n is 4, we'd have 2 to the fourth power, which is 16, and then so on forever. Well, that's just going to keep getting up. We're just adding more and more and more terms. If I wanted to cut it off and say S sub 3, that'd be the summation of the first 3 terms for this sequence, which is 2 plus 4, which is 6, plus 8, which is 14. And we just keep adding more and more and more. So the entire thing, S sub n, is going to infinity. And it diverges because it just gets bigger forever. And the same thing happens with number 2. And so I'm just going to go ahead and go on to number 3. Exact same type thing is happening with number 2. Number 3, slightly different. So number 3, come up with the first few terms. If we plug in 0 to n, that'd be cosine of 0, which is 1. Then plus, plug in 1, that'd be cosine of pi, which is -1. And then plus, plug in 2, that'd be cosine of 2 pi, which is back to 1. And plus, plug in 3, that'd be cosine of 3 pi, which is another -1. And plus dot dot dot. It would just keep doing that over and over and over again, over and over and over again. So I know if we just we just did s sub 4, that'd be 1, -1, 1, -1. That would be 0. So if we stopped it there, that would just be 0. But I mean, this one is oscillates forever. And so it's not actually approaching something. For the limit to converge, the limit of the summation, we are summing something up forever. For it to converge, the summation of all those values has to actually approach something, and it's not approaching anything. If we added one more, s sub 5, the summation after 5 terms, then that's a +1. Summation after 6 terms, that's back to 0. It's just going back, and the summation is just going back and forth from 1 to 0. So it doesn't approach anything. So usually divergent ones are rather easy. Most divergent ones are rather easy to spot. Whether something will be convergent or not is often a little harder. So on number 4 and 5, come with some of the first few terms. On number 4, we have 1 over 2 to the n power. Well, if n is 1, that's just 1 over 2. Then plus, plugging in 2, that's 1 over 2 to the 2nd power, so 1/4. Then plugging in 3, 1 over 2 to the 3rd power, so 1/8 plus 1/16. And that's just going to keep happening forever. We're asked to write first 4 terms. Did that. S sub 1, S sub 2, 3, 4, S sub n, and then the limit as S sub n approaches infinity. Well, that means the sum of until we get to the first term, or the sum until we get to the second term, and so on. So S sub 1 is just the 1/2. S sub 2 is adding the first 2 terms. So what is 1/2 plus 1/4?
3/4.
Yeah, 3/4. Okay, S sub 3, that's adding the first 3 terms. So 1/2 plus 1/4 plus 1/8. Or we can just take the previous sum of S sub 2 and add the next term. So taking 3/4 and adding 1/8. And that is going to give us, well, 3/4 is 6/8. So we just multiply top and bottom by 2. So adding 1 more eighth gives us 7/8. Then S sub 4, same idea. Is adding the first 4 terms. We're just taking the previous summation of 3 terms and adding the next. So adding 1/16 to 7/8. Well, we multiply top and bottom by 2, we get 14/16. Then add the 1/16. S sub 4 is 15. This right here is asking for S sub n, meaning it's some general term expression that would represent any nth term in this sequence. Well, if we look at this one right here, we ended up with 15/16. Well, we know the bottom. We got the bottom by doing 2 to the n power. So that's still going to be the bottom here. How can we get to 15? Well, when we do 2 to the n power, we got 16. So what can we do? to get 15, it's going to be 2 to the n minus 1. And does that still work for the other ones? Well, the third term, 2 to the n minus 1. 2 to the n for the third term, it would be 8 minus 1, so 7. Okay, we did have 7 on top, and 2 to the n on bottom, so 2 to the third, 8 on bottom. So yeah, so that's the general term here. Then we're asked to find the limit as n approaches infinity of s sub n. Well, then that's just taking the limit of this, the limit as n approaches infinity of 2 to the n minus 1 over 2 to the n. Well, as you get close to infinity, that minus 1 is pretty much negligible. Almost nothing is happening because of that minus 1. And so the limit is 1. On number 5, we have 0.9 plus 0.09 plus 0.009 plus 0.0009 plus ... And they didn't give us the summation rule here. We could figure out, we don't need to right now though. For us to find s sub 1, s sub 2, 3, and 4 like we did on number 4. So s sub 1, well, that's just 0.9. S sub 2, sum of the first two terms. Well, 0.9 plus 0.09, well, that 0.9 would just get added to that 0, so it's 0.99. Similar would happen here. You'd have 0.999. Then sum of all first four terms is 0.9999. Then, for us to find an expression for s sub n, well, meaning what the sum will be to the nth term, and that's pretty much just 0.9 repeating. Then the limit is an approaching infinity of s sub n. Well, the limit as that goes off to infinity would just end up being 1. So that's how to take partial sums, some partial sums. And both of these two did end up being convergent. The summation of these values approached 1. Because s sub n represents the sum of n many terms. We find that the limit as n approaches infinity, so if we have infinitely many terms and we're adding them together, we got 1. And the same thing happened with number 4. So both of these were convergent. And as we go throughout this unit, we're going to have a bunch of different tests that will determine if something's convergent or not based on a certain scenario or looking at different terms in the series. A few rules that can be applied to any series. If we already know that if we have two convergent series that we do already know are convergent, then the sum from 1 to infinity of a of n equaling a, and sum from 1 to infinity of b of n equaling b, and where c is just some constant real number. So if that's the case, and we know they're convergent to a and b, well, if you have the sum from 1 to infinity of c times a sub n, well, that c can essentially just be pulled outside the summation. And then it's just c times the summation from 1 to infinity of a of n. And we already know it's convergent to a, so it's just c times capital A. And then summation of adding two sequences, well, that can just be split up. And it would just equal whatever the summation of a is plus whatever the summation of b is. And then the same thing works with subtraction. All three of these rules are very similar to three rules we've talked about, before when we're talking about integrals. Because what is an integral? An integral is just an infinite sum. An integral is an infinite sum, and that's so if we can apply these things with an integral, we can apply them here with a summation as well. Okay, on the next page. So the first term we're going to talk about, you may have gotten it or may have not gotten to it yet in Khan Academy, is the Nth Term Test. But actually, before we do that test, one thing I want to discuss first is anytime we do any of these tests, we have to show, all these tests have hypotheses. They only work if some scenario is happening. Then you have to apply the test, and then you'd have to say what test that is. If you were going to use one of these tests to show that it's convergent or divergent on the AP exam, then you can't just use it and not say you used the test. You have to say why you can use that test and which test you are using. I have found out that a lot of students in the past are not doing any of that, and so losing points on their justification. So as we go throughout this unit, there's a few things we want to remember. For each test that we do to see if something's convergent or divergent, for each test you perform, you have to show that you can, C-A-N, do the test, that you can do the test. And so C-A-N is going to be an acronym. Meaning first, you need to list the conditions of that test. So if you're to do one of these tests on the problem or on one of these problems in the packet when you practice, on any sort of problem when you practice, on the AP exam, on free response questions I give you for when we start reviewing, you have to state that you can do it. You got to show that it's even possible to do that test. And so list the conditions of that test. Then actually apply all parts of the test. That's where the B and the A come from. And then name, that's name what series, what the series does by that test and by what test. Name what the series does, meaning does it converge or diverge? Or name what the series does, either converge or diverge, and then by what test. You have to say what test you're using, say whether it converges or diverges, apply all parts of the test, and before you can even do the test, list the conditions that show that the test even works. And I will do this throughout the problems I do as well. Anyone you see doing the problems, such as Sal Khan on Khan Academy or the other AP teachers on the YouTube channel, they'll do these things as well. Okay.
So are the tests only for convergence and divergence?
Yes, that's the whole point of this.
Okay.
Whenever we talk about any of these series, we are trying to figure out whether the series converges to some finite number or whether it diverges. And if it diverges, it's most likely either going to infinity or it's just going back and forth, oscillating forever.
Okay.
And so the whole point of this is to figure out whether it converges or diverges. There's a few things you can do with a certain different kind of series when we get to Taylor polynomials and power series. But really, if you have a series, that's usually what you're going to be asked about. Most of the series, even if you find out it can converge, you still cannot find out what it converges to, what value it converges to. When we talk about geometric series in a little bit, you can find that out, or you may have already done geometric on Khan Academy or remember it from other places, but there's a formula to find the sum of geometric. And there's one other type of series as well that you can find the sum to. But most of the series, even if you do find that it does converge, you may not, it's possible you might not be able to figure out what it converges to. And they probably won't even ask that unless it's geometric. If it's geometric, they may ask what it converges to. But if there's a free response question that has a geometric series or any really sort of series, and you have to show whether it converges or diverges, you would need to list all conditions and all parts of the test when you apply it, say whether it converges or diverges, actually answer the question, and then say what test you used. And I'll continue to show this as well as we do problems. And the first test we're discussing is the Nth Term Test. So these are convergence tests that we are starting. Convergence tests, which say whether a series converges or diverges. And the first test we're discussing, well, one other thing on just any of the tests is that there is no one test that will determine convergence for all series. There's no one test that will determine convergence for all series. So that's why we need to learn most of these. Some of the tests are used based on the certain form that the sequence is in. Some of them, certain tests are used if it's more complicated or based on certain things you're asked to do with it. But there's not just one test that's going to work for all of them. So the nth term. The nth term test says that if the sequence, A sub n, if the sequence does not converge to zero, if the sequence does not converge to zero, then the series diverges. If the sequence does not converge to zero, then the series diverges. And then, if the sequence does converge to zero, the series could converge. The series could converge. So essentially, this test is just eliminating obvious divergent series. The nth term test essentially just eliminates obvious divergent series, such that if it does not converge to zero, it just automatically diverges. If it converges to zero, it could converge, but it's still not official. If it does converge to zero, it still may diverge. We don't know, but it automatically diverges if it does not, if the sequence does not converge to zero. And so, just to sum those two phrases up together, if a series from 1 to infinity of a of n, if it does converge, then that means the sequence must have converged to zero. And if we see that the nth term test does not eliminate it, saying that it diverged and it just couldn't converge, we still don't know for sure whether it converges or not. Another test would be necessary. Okay.
Wait, Mr. Hunter.
Yeah.
So it says that if the series does convert or the sequence converges to zero, what does it mean by it could not, or it could converge if it just says that it
if a
converges?
sequence,
Oh, the
so
series.
just the list, the sequence is just the list of numbers. The sequence is just the list of numbers. So if the list of numbers converges to zero, then the series, which is the sum of the sequence, the sum of the numbers, could converge. So it either could converge or it may not converge. It's meaning that it's possible that it can converge. To get for sure, like that it actually does converge, we would need some other test for confirmation of whether it does or does not.
Okay.
The reason for that is, I mean, there are some sequences that the list of numbers could go to zero, but the sum of those numbers, it's still adding something enough over and over and over again that it would not go to zero.
Okay.
Such that the sum would not go to zero. And we look, we're going to skip some of the stuff down here. But essentially, the idea is that if we're adding an infinite number of terms, they're all positive, the sum's just going to keep getting bigger and bigger and bigger. So the only way for when we add an infinite number of terms for the sum to actually approach some value, eventually we need to be adding almost nothing. Eventually we need to be adding almost nothing. So is it getting larger without bound, or is there some limit? That's the question that we're asking when we do these. And if the terms are not converging to zero, then there's just no way it can converge. So if the sum just keeps getting larger forever, which is what it says right here, so the sequence, if the numbers just keep going up, then there's just no way it could converge, because then the sum would also be getting bigger forever. Or even if the sum approaches, maybe the sequence just approaches the number 1. If the sequence just approaches the number 1 forever, No, actually, that is what these two are talking about. So that'll answer your question if we look at these two graphs. So this graph right here, this is just showing the numbers in the sequence n over 2n plus 1. And based on n behavior rules, as n approaches infinity, we know that this number in the sequence is going to approach 1/2. And it kind of looks like that right now, that it's approaching that horizontal line of 0.5. Not super close to it yet, but it will get really close to it. So this is just the dots showing the sequence of the numbers. And this sequence is not approaching 0, approaching 0.5. But if we were to take the sum of that sequence, well, first, the first few numbers, the sum's adding more each time, but eventually it's pretty much just adding 0.5 over and over again. Just adding 0.5 over and over again, or at least a number very close to 0.5. So even though a sequence converges, if the sequence is not converging to 1, then you're adding some finite numerical value over and over again, and then the sum would go to infinity, meaning diverge. But if the sequence does converge to 0, it's still possible. If the sequence does converge to 0, it's actually still possible that it could not converge, and it would diverge, depending on the different sequence. And we'll see more of that with some of the different tests. So let's look at how this is applied. Again, Nth Term Test is also right there. So we're just determining whether the following series diverges or possibly converges. That's the two options if we're using the Nth Term Test. Well, Nth Term Test can be used pretty much anytime, but it only tells us whether it for sure diverges. But if it doesn't automatically tell us that it diverges, we still haven't answered the question, because we're always wondering whether it converges or diverges. So in this one, if we come up with some of the first few terms, this is 1. If we plug in 0, they told us to start at 0 this time. And then if we plug in 1, that's then 4. We plug in 2, that's then 4 squared, which is 16. And if we plug in 3, that's 4 cubed, which is 64. And it would keep adding that forever. It would just keep adding forever. Now we can see logically it's just going to keep going up forever, so the sum is not approaching anything. But using the Nth Term Test, the limit as n approaches infinity of 4 to the n power, well, that is infinity. And since that is infinity and not 0, the sum diverges by the Nth Term Test. So we would say that the series diverges by Nth Term Test. I'm going to say whether it converges or diverges and by what test we're using. Okay. You all still hear me?
Yeah.
Okay. I heard something weird. I'm going to skip number C now. So on C, here's some of the first terms. Well, the top's just 3n, so we'd have 3, 6, 9, 12, and so on. The denominator is n factorial. So 1 factorial is just 1, 2 factorial is 2. So this term right here is just 3 because it's over 2. And then plugging in 3 factorial, that is 6. And then 7 factorial, not 7, 4 factorial. You'd then just multiply that 6 by 4, so 24. So this 9 over 6, I mean, that's 3 halves. 12 over 24, that's really just 1/2. Well, if we use the Nth Term Test, we're going to take the limit as n approaches infinity of 3n over n factorial. Okay. Now, can't use L'Hopital on this because n factorial is not really a function, but the idea, again, is just, is it top heavy or bottom heavy? If it's top heavy, it's going to infinity forever. It's bottom heavy. I mean, it's not rational, so we can't use the leading coefficients. But if it's bottom heavy, then it's approaching 0, and that's good and helpful, and that tells us something. So factorial is going to go way faster than 3 times n. And we can already see that here. 1, 2, 6, 24. That's growing a lot. The top only going up by 3 each time. Bottom's going up way faster. So factorial will grow way faster than 3n. So it is bottom heavy and is approaching 0. And so since this is happening, the series could converge by nth term test. Not really. If we were asked to do this on a different problem, like actually on the AP exam or some pre-response question, this really wouldn't be good enough. We have another test that we'll get to later on that really will show whether this converges or diverges. Just saying it could converge doesn't actually answer the question. Okay. Next, different test.
So that wouldn't be an answer. Would that be an acceptable answer in the test?
So this is a sufficient answer since we were told on this problem just to determine whether it diverges or possibly converges.
Okay.
We have determined that it does possibly converge. Since the only test we've learned so far is the nth term test. So we've used the most amount of knowledge that we currently know to figure out whether it converges or diverges.
Okay.
But as we get to more tests, we'll be able to figure out more concretely, more exactly whether it converges or diverges. But that's all we could do on that problem. So we answered that problem as best that we were asked to.
Do we have to write out the sequence every time, like the first 4
no,
terms?
you would not. I just wanted to give you an idea of what was happening.
Okay.
Sometimes it's helpful visually to see that it is going more on the bottom than on the top. So you do not always have to write out some of the numbers of the sequence. I mean, one reason I did that here is it told us up here, so a basic strategy is to generate 4 or 5 terms, get a feeling of what the series is doing. So it's often helpful just to write some of the terms, just to get an idea of what the series is doing. Because on like A, writing the first 4 terms helped us automatically see, oh, it's just getting bigger forever very quickly, so it's going to diverge. Writing a few of the terms can also, once we see more of these, help you figure out which test to use. But no, you don't always have to. We were asked to here, and it is sometimes. Yeah. Next one. Telescoping series is not really a test. It's more of a specific form the series is in. But I mean, it does count as a test if you were asked to show that something converges or diverges. If something is a telescoping series, it most likely will. So if we've used the nth term test and determined that it could converge, we want to then use some other convergence tests because it's not good enough to show for sure. First one we're going to look at is the telescoping series. And the telescoping series does give us a quick decision on the fact that it will converge. And the general form of the telescoping series is what number 7 is showing here. That it's going to be adding a number, subtracting, adding, subtracting, adding, subtracting, such that a whole bunch of terms in the middle of the series will all cancel out. Almost every term in the middle of the series will end up canceling out, and you'll just end up with terms on the very beginning and the very end. And that's very helpful to see that here. And so if we have the series, we want to figure out whether it converges or diverges, and then possibly what it converges to. Apply the nth term test, Well, the limit as n approaches infinity of 1 over n minus 1 over n plus 2. Well, taking both those to infinity, both those fractions would end up going to 0. So based on the Nth term test, it could converge. It could converge. We don't know for sure yet, but when we see that a bunch of stuff will cancel, yeah, that'll be more obvious here with this sequence. So now let's expand the series to really see what's happening. If we plug in 1, that very first term is a 1. I'm going to put parentheses around each section. Minus 1 over 1 plus 2. So that'd be minus 1/3. So that's when we plug in 1. And plus, when we plug in 2, well, we'd end up with 1/2 minus 1 over n plus 2, meaning 1 over 2 plus 2, which is 1/4, so minus 1/4. And plus, when we plug in 3, we end up with 1/3 minus 1/5. And then we can already see a pattern happening here, that the first term in each of these parentheses, the bottom's going up by 1, and we're subtracting the first term, the second term in each parentheses, bottom's also going up by 1 each time, but it's just like 2 units away, the bottom number. So the next one's going to be plus 1/4 minus 1/6 dot 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 forever, and it's just going to keep adding those forever. Okay, so here we're asked for the sum of n many terms of s sub n. Well, let's analyze quickly what we can see happening so far. Well, we have 1, then we're going to subtract 1/3, then 1/2 minus 1/4. We have a plus 1/3 here. Well, this minus 1/3 is going to cancel with that plus 1/3. Okay, then we have a minus 1/5. We got a plus 1/4. Well, we saw a minus 1/4 over here. So this minus 1/4 is going to cancel with this plus 1/4. Okay, so some stuff is starting to cancel. And then we keep going. We now have a minus 1/6. But what would be the first term in the next one? First term in the next one would be a plus 1/5. The first term in the next series would be a plus 1/5, canceling with that minus 1/5. Then another set of terms later on, you'd have a plus 1/6, canceling with that minus 1/6. And almost all the terms in the middle would end up canceling. So at the beginning, the only 2 terms we did have was that 1 and that 1/2. But then what's going to be left over at the end? Well, what's always going to end up happening with these telescoping series is however many terms you do have staying alive at the beginning is how many terms you'll have staying alive at the end, is the second of each, as the second number of each of those 2 parentheses. So we add these right here. We have 1 and 1/2, which is 3/2, or 1.5. Then as we get off to all the way to the right to like positive infinity, we keep going. Eventually when we stop, we saw here, these 2 marks right here, that I was making, they were at the beginning of a set of parentheses. But the number, the back end of the parentheses stayed alive. The minus was still going to be there. And since we had 2 terms still alive at the beginning, we're going to have 2 terms still alive at the end. So we'll have minus on the last one. The very last one would be this last term there. That's going to be the very last one. Very last term that still works will be that last term there, just like the very first term worked. So we will still have a minus 1 over n plus 2. And then the second term in the previous parentheses is also still going to be there because that 1/2 was still alive. And so the second term in the previous parentheses would just be one before this one, which would end up being 1 over n plus 1. So the sum of n many terms would end up looking like this. We ended up with 3/2 left over at the beginning then we end up with these two terms left over at the very end. And then if we now take the limit as n approaches infinity of this right here, which represents the sum of n many terms, well, these two terms would end up going to 0, and we are only left with 3/2, or 1.5.
So, Mr.
And I
Henry,
wouldn't stop right here. I do need to say that it converges to this value. It converges by telescoping series test. And this right here is a pattern of what will for sure happen. Those last two terms, when we take it to infinity, they're going to end up going to 0 and cancel. So the only thing we were left with for the sum did end up being the terms that stayed alive at the beginning. What was your question, Zeus?
oh, so for a series like this, we have to expand the series.
We would have to expand it enough so that we could figure out which terms are canceling and which ones are staying alive at the beginning.
Okay.
So we wouldn't have to expand it forever. I mean, I clearly didn't need to put this last term because we could already see which ones were going to end up canceling and which two stayed alive.
Okay. Thank you.
But I did as much as I did so that I could show y'all what was happening. Okay. Essentially, the simplest form of a telescoping series is just some number minus another number, then the very next number is then subtracting that one. And then in this case, all of these beginning terms, that a sub 2 cancels with that a sub 2. That a sub 3 cancels with that a sub 3, and so on. A sub 4s cancel, a sub 5s canceled, and so on. Just like what happened with ours. And then at the very end, we have a sub n, you got a sub n minus plus 1, and so on, and just keeps going forever. Well, a sub n would end up canceling with the previous a sub n right before it. And you're just left with, and this one right here, we're just left with one number at the beginning and then one number at the end. And that one number at the end will end up going to 0 in these kind, where everything ends up canceling. So it's going to converge only if that, well, actually, I spoke ahead. This one that we did here, this a sub n value, these a sub n plus 1 and a sub n plus 2 values at the end did end up approaching 0, which allowed it to converge. But I mean, it doesn't necessarily have to do that. So a telescoping series is only going to converge if the a sub n plus 1 term approaches 0, which is these last terms. If that last term would approach 0 as n approaches infinity, then a telescoping series would approach 0. Okay, well, I have posted the key, so I want to go ahead and get on to the next unit. I'm in section 18, geometric series and p-series. So, a geometric series. Well, an arithmetic series is one that's adding the same thing over and over and over again, while a geometric series is multiplying. Well, geometric sequence. Both those terms, I should have said sequence. An arithmetic sequence adds the same thing over and over again. Geometric sequence multiplies the same thing over and over again. And again, a series is just a summation of a sequence. So if we've already seen that by the Nth Term Test, it could converge or can converge, we still don't know for sure whether it does or does not. And so we need some other test for further confirmation. And so next one we're looking at is a geometric series. So a geometric series is going to generally be in the form of summation from n equals 0 to infinity of a times r to the n power, where r is the common ratio, whatever it's multiplying by over and over again. You can see that if I multiply the first one by r, I get the second term. Multiply the second one by r, I get the second term. So on. It's just multiplying times r over and over and over again. That's a geometric series. sequence when it's multiplying this by the same thing over and over again. So R represents that common ratio. R is the common ratio. A is just whatever beginning number you have. Is whatever beginning number you have when R is 0. When you're when n is 0, your 0th term. Okay. Then here we're told if the absolute value of your common ratio is greater than or equal to 1, the series will diverge. If the absolute value of R, which is your common ratio, is greater than or equal to 1, it will diverge. If the absolute value of your common ratio R is less than 1, then it will converge. And we even have a formula for what it will converge to. That it will converge to A over 1 minus R. So telescoping series and geometric series are actually the only two series that we can figure out the value it converges to. So other than telescoping, geometric series is the only other one that you can figure out what it converges to. All the other ones, we just figure out whether it converges or not. So if we look at a few of these, I will not do all of them. We're going to do 1, 2, 5, and 7. So looking at number 1. Well, again, you don't have to write out the first 4 terms all the time. This is asking us to. It's very helpful. They wouldn't ask you to do that on the AP exam. It's very helpful to see what is happening. So I'm going to write out the first 4. So when n is 0, well, something to the 0 power, that's just 1. Something to the first power is itself, so that's 2/3. Then to the second power, we're squaring top and bottom, so 4/9. Then the third power, we're cubing the top and bottom, so 8 over 27. It's just going to keep adding forever those values in that sort of pattern. Well, in a geometric series, we are told that it will diverge if absolute value of R is greater than or equal to 1, and it will converge if absolute value of R is less than 1. So in order to determine whether it converges or diverges, we have to identify what R is. So if you use the geometric series, and if you identify that it is a geometric series, you have to state what the R is. So what is the common ratio here that it's getting multiplied by every single time?
2/3.
Yep, it is 2/3. So R is 2/3, which is less than 1. And since R is 2/3, that means so it will converge. So I spelled series wrong. SERIES. Here we go. So the series converges by geometric series test. And we are told here that if it does converge, to also find the sum. So we'll now use that formula such that the sum S would equal A. The A value here is whatever the 0th term would be at the very beginning when n is 0. And so our A value here is just 1. And so we end up with 1 over 1 minus R, which is 2/3. So 1 over 1 minus 2/3.
Sweta!
And then now
You distracted me.
From what?
I forgot about this Zoom meeting. Shoot. Oh my God, I'm not on mute.
And now we're going to multiply everything top and bottom by the denominator, which is 3. The easiest way to simplify that. So that gives us 3 on the top. And then that would end up being, if I multiply that entire denominator by 3, we'd end up with 3 times 3 minus 2, which is 1. And so the series converges to 3. Now on number 2. Number 2, though, when n is 0, it's again starting at 0. No, that was dumb. Starting at 1 and plus 3/2, because when n is 1, that's itself. Then 9/4, then plus 27 over 8. It's pretty much the flip of that one. Well, what is the r this time? This time, r is the 3/2. So r is 3/2, which is greater than 1. So it diverges by geometric series test. And yes, you can simplify it to geom. I've seen AP graders do that when I've watched their stuff. Next, we're number 5. Number 5. On number 5, we have when n is 0, we'd be raising this fraction to the 0th power, which is just 1. So we'd start off with just 8. And then when n is 1, it'd just be this itself. So it'd be 8 times -3/4, which would be minus, well, what's 3/4 of 8? That would be 6. Then when n is 2, well, that would become positive, and we'd be squaring it. So 9 over 16, and then that's 8 over 16. That'll simplify to just a 2 on bottom, so 9/2 plus 9/2. And then when n is 3, we'd end up with a -27 on top and a 64 on bottom. 8 over 64, we end up just with an 8 on bottom. So that would end up being -27 over 8 plus ... Okay. Well, so that's what's happening there, and it's kind of hard to tell what is happening just based on those numbers. So what is the r that it is getting multiplied by over and over and over again? Well, that will be the parentheses. Whatever's being raised to the power. What's being raised to the power when it's in this form is your r. Because as we see earlier in the formula, the form of a geometric series is this. Geometric series sum from 0 to infinity of a, some constant a, times r, your common ratio, to the nth power. And so whatever term is being raised to the nth power, that is your r common ratio. So here that's going to be -3/4. So the absolute value of r equals -3/4. And the absolute value of it is less than 1, meaning it converges. So converges by geometric series test. And now we're also going to find the sum. Well, S would equal, well, sum formula is A over 1 minus R. Well, our A term here is 8. Put 8 over 1 minus a -3/4. And like I did on the other one, we will now multiply the top and bottom of this by 4 to help this out. And 8 times 4, that gives us 32. On the bottom, 4 times 1 over here gives us 4. And 4 times this fraction would just cancel, so we just have that -3. So we end up with 4 minus a negative is plus, so 4 plus 3. So we end up with 7 on the bottom here, and 32 over 7 ends up being the sum. Okay, and then let's look at one where they don't give us the formula. We got to figure out what it's changing by. And now number 7. Number 7, we have 4 plus 2 plus 1 plus 1/2 plus so on. Well, as I mentioned before, r is whatever number it's multiplying by each time. Whatever number it's multiplying by each time. So here, what is it multiplying by each time?
1/2.
Yes, good. So it is multiplying by 1/2 over and over and over again, times 1/2, times 1/2, over and over and over again. Okay, so that must be the R. We've already identified that our R is 1/2. And so will this one converge or diverge? Yes, it will converge because R is less than 1. So converges by geometric series test. So it does converge because R is 1/2. That's what it's multiplied by over time. And to figure out the sum, we're going to use the formula that S equals A over 1 minus R. We need to figure out what that A is. Well, A would be the 0th term. A is your very beginning term at the beginning. But another way to figure out A, we just factor out that beginning term. We factor out 4. We then have 1 plus 1/2 plus 1/4 plus so on. Okay. And so the thing that is multiplying by the entire sequence is the 4. So that 4 must be the A value. So S would equal 4 over 1 minus 1/2.
Mr. Hunter.
Simplify it. And multiply the top and bottom by 2. From the top would give us 8. The bottom, 1 times 2 is 2. 1/2 times 2 is just 1. So we'd have 2 minus 1, which is 1. We just end up with 1 there. And so the summation is 8, and it converged by the geometric series. Okay, well, this has gone longer than I anticipated, so don't want to keep you much longer. The key to section 17 and 18 I will post as soon as we are done here. And I'll finish going over this section and go into the next sections that we will do next time we meet. And the next ones will continue to be at 1 like today.
Mr. Hunter.
Yeah.
So for a geometric series, do we always assume that for the one that we showed where it was just the numbers adding up, the last one, do we assume that the initial n value is 0? So if we're having to figure out what the series is starting at, then if we're having to figure out what the series would start at, oh, no, the A value is just whatever's multiplying by it all. So. No, the n value.
What? The
oh,
n
yeah.
value?
Yeah, sorry.
Oh, the beginning one, if we're having to figure out our own series, it really wouldn't matter whether it's 0 or 1. It really wouldn't matter. So you could consider it 0, you could consider it 1. It wouldn't change what's happening. Because the idea if we see that it's multiplying by the same thing over and over, that automatically makes it geometric. Whatever that is, whatever that common ratio is that is multiplying by the same thing over and over, that's then your R, which can tell you whether it converges or diverges. It's the beginning term. Whether your beginning term is when n equals 0 or your beginning term is when n equals 1, that beginning term, that's your A value. The A value is just whatever's being multiplied by everything in front, and is also the beginning term. And so if you have your own series where it doesn't give the summation symbol, then it doesn't matter whether you call the first one 0 or 1.
Okay.
Any other questions?
You were saying next time we'll just finish up 18 and move on to whatever next.
We're skipping section 19. I don't know if I included that in the packet that I put online or not, but we are not doing the integral test. You almost never want to do it anyways, but because it's very frustrating to use and uses improper integrals. So we're not going to use do the integral test at all because it's not on the AP exam this year. It doesn't really pertain to any of the other tests. It's not similar to any of the other tests. So we're skipping section 19. And so on Monday, I'll cover P series and then move on to the comparison series tests of section 20 and then 21 on Monday. And as I said earlier, the YouTube channel link I sent out earlier is this morning. And that's also the same link. I don't remember which day I put it on, but I have that same link also on the calendar. But that's also a great resource. Keep in mind, I'm not going to grade what you're using on Khan Academy and which problems you're doing on Khan Academy. It's just another good resource to be able to learn this unit in a timely manner. And if we hopefully do come back week of April 13th, we'll test over this unit sometime that week, but it will be a test more similar to what you could expect on the AP exam of only those kind of series, sequences and series.
If by similar to the AP test, does that mean that it's only free response or will I have multiple choice?
I will probably not have multiple choice on that test because you won't see multiple choice on me. You probably will not see multiple choice again this year other than the TEKS test if that happens. Or the final exam if that happens and if you take it.
Okay.
Any other questions before we end?
So if the AP test isn't going to do a calculus subscore, does that basically mean they're only going to test over BC units, like those purple units?
It does not mean that.
Oh, okay.
So because Calc BC has always been considered Cal 1 and 2. It is not considered only Calculus 2. And so they wouldn't only do BC material. There will probably be a significant amount of BC only material, such as integration by parts, improper integrals, partial fractions, Wright-Euler method, logistic. I mean, they'll probably definitely want to do logistic this year. So, I mean, they could even base it off of the coronavirus. But there will still be AB material on there. I don't understand why they've chosen not to do. I don't understand why they've chosen not to do the AB subscore, and we may find out more about why that is next Friday. So they've said that a lot more information will come out next Friday about the exam, more specifically on what kind of questions and what they're expecting. I don't know if they're making a practice test specific to this year or not. I have some practice tests that other AP Calculus teachers have made, and so of what they think this year's test will be like. But I will know a lot more about the exam next Friday, April 3rd. Because they also haven't even released what are the two test dates. One test date will still be in May, probably around the normal original test day time. And then one will be later, but they haven't released that. They'll release that next Friday, April 3rd. Any other questions? Okay, well, guys, don't work too hard. Still enjoy yourself. Be a kid. Take advantage of this time. Relax. Play video games. Watch TV. Just do some calculus, a little. And there's plenty of resources. And I know you probably miss school. I don't know why you wouldn't at this point. And I miss it as well. And miss actually seeing you and people in general. So have a great day and a great weekend.
Bye.
Cool, going to Princeton.
Awesome. Is that the only thing on? You say I'm not reading the chat. I've seen very few things on the chat. I only see 4 people saying anything.
Oh, they were spamming earlier.
What?
Yeah. Bye, Mr.
Okay. Well, bye.
Hunter. How do I leave?
Well, I'm just gonna end it.